How do you tell the difference?
Oh, I can tell. Actually, yeah.
You're going back to the whole like
It's
why?
2016. That's just a jacket.
You're going back to the whole like why buttons are on opposite sides for girls and guys clothing.
That is right though. They are. Yeah.
Well, because the men used to be dressed and the women used to be dressed by other people.
What?
No, it's the other way around.
The women used to be dressed by other people.
Yeah.
Well, meant some kings got dressed by other people, but they'd stand behind them. For women, it was they'd stand in front of them. When you're a king, you didn't dress yourself.
I still can't dress myself.
Still wouldn't say.
Andrew.
I think the cheerleading team picks out your outfits now.
That is true. That is true.
My problem with like things that haven't been watched yet. All the buzzes there. What is it?
Oh.
I haven't watched it yet.
Should we get one of those name orders?
It's a Walrus one.
Yeah.
It's actually really fun.
I don't know. We might not do what they said.
Yeah.
Right now we missed our chance, dude.
Yeah, we can bring it back.
I don't even know how to do it.
Well, no, but like, because at the other semester, they have elections for the new officers. So it'll be our class.
I'm not doing
It'll be
it.
fine.
I would say it'll be our class, so like,
Yeah.
whoever's in charge, we can do it.
It's non-existent.
Really?
It's really not technically
Andrew,
What's
I'm
up?
gonna run for Liam's position of
Of what?
food guy.
Is that what he is?
His position literally is order food.
Sounds like too much responsibility for me.
It seems like the easiest job in the world.
Yeah, Jackson's chow team commander should be doing that.
Well, they're about to run against me, and I also speak just about getting good.
Alright, a couple quick things. Number one, I saw like 5 of you guys have done it so far. The midterm teaching evaluation forms that the College of Engineering sends out. Please do fill that out. If you send me an email with a copy of the confirmation that you submitted it, I'll check you off and give you 5 points back on the cumulative homework. So five extra credit homework points for doing so. Number 2 is if you didn't get your test back to me on Wednesday, swing by office hours after class and I'll give it back to you there. So today we're just going to do a couple or 2 examples with what we've been talking about this week, namely conservation of mass, conservation of linear momentum with control volumes. So we showed this little, well, I'm supposed to play. Whatever. All right. At the beginning of the conservation laws lectures, I showed this little video. If you take a jet of water and you spray it with increasing velocity at a vertical block, at some point the block tips over. This should be pretty clear. So to figure out actually to analyze this problem, we're going to boil it down to a simpler case. Shown here where this guy, namely you, holding a plate against a horizontal water stream. And the goal of this example is going to be to show you how your choice of control volume doesn't ultimately matter in giving you an answer, but it can simplify or complicate the steps that you have to go through, or increase the number of steps that you have to go through in order to get your final solution. So with this problem, we're given that the inlet here has a speed of v1 and a jet area of a sub n, whereas the area at the plate here is a sub p. And we're supposed to find horizontal force on the hand. We're going to do this with the 2 different control volumes, 2 ways. So before we let me Okay. So, given for this problem, we have V1 AN, which is the cross-sectional area of the jet here, AP, which is the area of this plate, and what we're finding is the force exerted by this system on a hand that is holding the stem of this plate here. So, if we consider, I wish my black marker worked.
So, can you explain what this is again?
This is,
Just kind of zoomed out.
yeah, let me just pull this back up. So imagine you've got like, I don't know, just a circular, like shaped flat plate with a stem sticking out of it, right? And you're just holding it up against a jet of water. The idea here is we're trying to calculate what force this plate is going to exert on your hand, you know, what the reaction force, or the reaction force from your hand would be on the plate to hold it in place. So we're going to do this problem with two control volumes. The first, I'm trying to make this as this isn't useless. Alright, well, anyway, control volume 1. Let's go ahead and look. Something like this. And control volume 2 is going to look something like that. So, first things first, before we actually go about analyzing these, our governing equations. What are the two we've talked about this week? Just call one of them out by name, you know.
Conservation of mass.
Conservation of mass. Which we write as 0 equals time rate of change, integral over the control volume, the rho dv plus integral over the control surface, rho v dot n dA. Alright, and the other governing equation, conservation of linear momentum, yep. Which tells us that sum of the forces, that is the surface forces plus body forces on the control volume is equal to control volume rho v dv plus surface Okay. So we've got given, find, sketch the problem, and our governing equations. Next step, go through this systematically, is what assumptions can we make about this problem? So. Did they say anything about a time varying quantity here in this problem statement? Is there anything here indicating that stuff's changing with time? No? No? So it's safe to assume we've got steady flow. In the problem statement, actually, it did say, I don't know if you're going to be able to see it over the... Alright, it's not given in this slide. We're assuming incompressible and homogeneous flow. That is, rho equals constant, and we're assuming that inflow and outflow is uniform. That is that V1 doesn't have some changing velocity profile across the jet. Okay? So these two will come into play in just a minute. But first things first, steady, right, allows us to kill anything that has a DDT term on it. Equations. So this and this go to 0. Which leaves us with steady conservation of mass and steady conservation of linear momentum. Alright? So let's go ahead and summarize this a little more compactly. Alright. Let's start with control volume number 1. Alright, and let's kick this off with a, so we've got CV number 1. Just like with any time we're computing forces, start with a free body diagram. So we've got our control volume. Right. Start with the body forces. I was saying body forces are caused by what? Remember, body forces as opposed to surface force. We've got a fluid element. Surface force is caused by things pushing and pulling on it, like fluid pressures, shear stress. Body force might occur in gravity or magnetic field. Remember, it's just, in this case, the body force acting on the control volume is just going to be weight, where it's equal to the weight of the water in the control volume plus the weight of the plate itself contained in the control volume. Right? We're going to neglect air here because it's so light. Surface forces. What's pushing and pulling on the sides of the control volume here? Anyone wanna? What about pressure? Well, I mean, there's pressure, right? We haven't said anything about, you know, using gauge pressure here. So for the sake of generality, and this is actually going to become important for this problem, we're going to assume that we've got atmospheric pressure acting on all the faces, right? Finally, anything else? Anything else pushing on the control volume? How about this f of x, the hand that's holding the plate in place, right? What we've really got is we've got the edge of a plate sticking out of this control volume, or the stem of a plate, with a hand holding onto it and pushing on it, right? So we can be pretty sure that this force is going to be acting in this direction, but it's good practice to just put it in the reaction forces, to put them in, draw them in as positive, and the signs of these will sort of come out in the wash as we go through the problem. So Rx and Ry are the forces of the hand on the control volume, pressure forces acting on surface control volume, the weight of everything inside the control volume. Okay, black box. We're not looking at what's actually going on inside here. We're just looking at the box that contains our entire system. So, the question asked for f of x, right, or fx, which means we're only concerned with the horizontal direction. So we're going to do, we're going to look at conservation of linear momentum in the x direction only. So, sum of the forces in x is equal to surface rho in the box. What's going on here? Is it velocity? I'm only looking at the x component. Right? That's right. The linear momentum in the x direction only, which means that I want only the x component of the velocity. So in the x direction, we've got, is our body force here, is W have any component in the x direction? No? Okay, so no body force. We've got then Rx plus, what's the pressure force acting on this face? Let's go ahead and define say that this thing has a area, control volume area on this face, right? And it's constant on both sides. So we've got P atmosphere times area, projected area of that side of the control volume, minus P atmosphere. Man, I'm gonna run out of room. Is equal to integral of thing here. All right. We gotta get rid of our free body diagram. Give myself some more room. let's look at this term here, the v dot n. On the inlet term here, right? In which direction does the normal vector point? The negative x direction, right? We've got should be negative 1i, yeah? And v1 points in the positive x direction, right? That is, at the inlet, we've got inlet, we've got v1 equals v1i is equal to ui, right? And n hat equals negative 1i. V dot n, therefore, is going to give us negative v1 or negative u, alright? If we consider the outlet, where the things are flowing out, we could go ahead and calculate v dot n, but what's u at the outlet here? At this point and this point. U is 0, right? So those integrals disappear. So if we split this into an inlet and outlet integral like we've been doing, yeah, where we say this is integral, equal to cs in dot 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 plus integral over cs out dot dot. It's all this dot 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 that goes to 0, so we can ignore the outlet entirely. So all we have to concern ourselves with here is the inlet. Okay? So now, with this relationship, we've seen that if v dot n is equal to negative u, if we put that in, and we say now, also, hopefully you can see that these two terms cancel each other out. We've got integral of the area of rho negative rho u squared dA. Right? Now, here's where we get to take these two assumptions. Say rho is constant and the inlet and outlet flow are uniform, meaning this integral, this remains constant, and over the inlet area that we're integrating, u here remains constant as well. We should say cs inlet. So we can move both of these outside just to give us negative rho u squared integral cs in dA. What's the area of our inlet? Right? We were given the A sub n is the jet area where it crosses the control volume. So we have integral of dA is just the area. We get negative rho u squared a n. Okay. So that's the force pushing on the plate, right? That's the force pushing on the edge of this control volume. The only thing to recognize here, and this is essentially our answer, but the only thing to recognize is that, for every force equal opposite reaction, such and such. The question asks for the force on the hand, so just remember that if the hand is exerting this force on the plate is exerting the negatively signed version of that on the hand. Yeah. So the solution of the problem ends up being positive, rho u squared a sub n. Sanity check. Does this make sense? Is the sign right? If I'm holding this plate here against a jet of water coming in, if x is this direction, the force that I'm feeling is in the positive direction? Yeah. So it makes some sense that we end up with something that, remember in our Bernoulli equation we had the dynamic pressure, right? The stagnation pressure involved 1/2 rho u squared. Does it make some sense then that we have a rho u squared term in here? Something about dynamic pressure and stagnation. Alright. So now, So for control volume 1, summarize that. So for CB number 1, the steps we went through here were free body diagram on control volume, conservation of linear momentum, answer x equals rho u squared a n. For control volume 2 now, differences from control volume 1 are the area here has shrunk, so now the right hand side of the control volume is the surface of the plate. Alright, this control surface is bounded by the plate, whereas before it enclosed the plate. So our free body diagram, CV number 2, let's go ahead and do our body diagram. If we have our, let's make that bigger. Control volume. Alright. Body forces. What do we have acting on this thing? Weight of the water. Is the weight of the plate involved this time? No, right? None of the plates in the control volume. Good. Weight, H2O. Surface forces. We've got, well, once again, we've got a reaction force here, right? X, Ry. This time, it's the force of the plate on the control volume, right? Because the control volume no longer contains the plate. As a result of the plate being on the side of the control volume now, if I draw the pressures acting on the control volume, you know, I still have atmospheric pressure here. I have atmospheric pressure here. Atmospheric pressure here. And I don't have atmospheric pressure here, right? We're assuming this thing's got like an airtight, you know, perfect bond with the plate. Okay?
Friction?
Huh?
What friction?
Well, we're assuming inviscid here. There's no friction going on. There wouldn't actually be a whole lot of friction. Well, there could be between the water and the plate here, but for right now, we don't need to worry about that. So difference here now is, whereas before we had, you know, equal pressure forces on all sides of the control volume, now we've got this imbalanced force. So we've got H2O, we've got force and pressure, and we've got reaction force, right? So I don't know why I did this table. This was a stupid idea. Let's do sum of the forces in the x direction, okay? Which is equal to forces, surface forces plus body forces. Surface forces here. We've got in the x direction, the area of this thing now is a plate, right? Because we've made this the same, like an extrusion of the plate surface. So we've got the pressure force is equal to the atmospheric times area plate. There's no canceling pressure force in this time. Plus our x is equal to our conservation of linear momentum term, right? Anything else going on in the x direction? You can see. Let me know if I'm wrong. I miss things, but I think this is all we need. All right. So we go ahead and split this up again. Let's go ahead and get a little more expansive this time. We've got P atmospheric times P plus Rx is equal to, we'll say the inlet, rho U V dot N dA plus integral over the outlet, rho U V dot N dA. Once again, inlet. Has anything changed about what we have at the inlet? Not really, it just moved upstream a little bit. But we have V1 dot N is still going to give us negative V1, right? Negative V1 or negative U, okay? Outlet. Here and here. Anything going on? No? Nope. This term still goes to 0 because there's no horizontal velocity at the outlets. So once again, we can say that this then is equal to integral over S1 rho U squared dA. We can take the knowledge that rho and U are both constant over the inlet area. Move this back outside. And what we end up with is equal to, it's equal to negative rho U squared A N. Right? Well, this looks like what we got over here, so you might be asking yourself, like, what's the big deal with the choice of control volume? But look at what we have on the left-hand side now. If this is equal to Rx plus P atmospheric times AP, then now we have that Rx. We have that Rx is equal to negative rho U squared AN minus P atmospheric area of the plate. So we're getting a different answer than we were before, anyone feel like hazarding a guess why that is? Like, well, first off, is this the answer we're looking for? Is this force what the problem asks for? No, right? What does this force represent? What is this Rx?
Pressure on the plate.
Or the force of the plate on the control volume, right? And the problem statement asks for the force of the plate on the hand. So we've gone this far into the problem. We need to take it a little bit further. And to do that, let's go ahead and do a free body diagram of the plate itself. Okay? So things that are acting on the plate. Well, now we've got the force exerted by the hand, as well as right? Atmospheric pressure acting on this side of the plate. Again, this side is absent because it's up against this jet of water, right? We're already accounting for the force on this face through the force of this face and the transfer through the reaction force here. So if I say, okay, I'm interested in some of the forces in X, some of the forces in X on this thing, how do we calculate the pressure force on this, right? It's a curved surface. We simply project out the area of this thing in this direction, right? If we were to integrate the pressure with the normal direction all along the outside of this thing, what we'd end up with is that force due to pressure is simply equal to P atmospheric times projected area of the plate, that is.
Which is there a vertical force too?
Well, the vertical force, the thing is we're just not calculating the vertical force because we're only looking for the horizontal component. If the vertical force were here, well, we may as well draw it in. There would be a body force, and the pressure force, if we're in air, like it's going to be minimal, right? That was the, if it were underwater, you'd have a more significant buoyant force, but as that exam problem pointed out, in air, even with a fairly light object, it only changes the apparent weight by like 0.25%. So if we do sum of the forces in x, we have now negative the atmospheric times area of the plate plus force of x equals anything moving? Right? Is there any acceleration going on? The whole system's holding still, right? Equals 0. Okay? Oh, wait, I forgot something. The force of the control volume acting on the plate, right? I need this reaction force here to show up in this problem as well. So, Rx.
Isn't R sub x pointing in the negative direction though? No.
In this case, it's, well, no, it's not going to be.
So that's negative R sub x acting on the plate.
Because remember, R sub x is shown pointing in this direction, but we have a negative sign on it, right? And so, and I like to draw them in always positively signed, and then just include a plus or minus sign, right? And I mean, this makes sense. The jet of water is going to force here. So, let's go ahead and make some room. And write this out a little bigger so you guys can actually see what's going on. So forces equals 0. We've got R sub x plus fx minus P atmospheric times AP is equal to 0. Rx is given over here, right? We're going to have the negative of the R of x over here, so plus and plus. So we're going to have rho u squared a sub n plus P atmospheric AP plus Fx minus P atmospheric AP equal to 0. Well, we've got plus and minus the same term here, so we can cancel those out now. And if we move f of x over to or move this over to the right hand side, we get f of x now is equal to negative rho u squared sub n. Once again, this is the force being exerted on the edge of the plate. The question just asks for the force that the plate is exerting on the hand. So once again, we just change the sign on this, and we get the same answer we had here. So for control volume 2, to kind of summarize the steps we had to go through, we said, all right, FBD of the control volume, which led us to conservation of linear momentum, which led us to FBD of the plate, which then led us to our answer, f of x equals rho u squared a n. So we had this one extra step involved, just because we changed the control volume. So the goal here is to illustrate 2 points. Number 1, the control volume doesn't change your solution, right? It's an imaginary box. No imaginary box you draw around this is going to change what's happening with the physics of the system. But if you're smart about how you pick the boundaries of your box, then you can simplify your analysis a little bit. You can skip a step or two. In this case, having one of the control surfaces cut through the point where we're trying to calculate the force means that we're actually directly accounting for that force's influence on the control volume itself, instead of having to go through the step of load transfer through the plate. Okay? So, any questions on this? Sorry, I'm not super great at keeping it well organized. All right. No, we're not gonna have time to finish this one. Yeah, there's not a chance we're going to get through the next example problem before the end. So, we got 10 minutes, right? Yeah. Any questions from the stuff we've covered so far? Yeah.
So like, I know this example is just one example, but like, would a general rule of thumb be, it's better to like include everything that has like a force acting on it in the control volume, or
It would.
just a case by case?
It's a case by case, but as a rule of thumb, include everything in the control volume that you would consider like an intermediate result. Like in this case, we don't care about what's going on between the plate and the water. We're saying, if we're going to treat the control volume as a black box, let's make it work for us and try to sort of swallow up all of the interactions going inside of here and just focus on the thing we want.
Okay.
Okay? All right. So, is there anything? Were there any questions remaining from the kind of the exam review that we did on Wednesday? Would it be of use to anyone to kind of go over with a little more time that last problem? I guess. Show of hands if you think, yeah.
About the exam, about the practice exam, are you gonna post solutions next time to the practice exam?
The practice exam. I could post solutions. Yeah, if that's something that's going to be helpful. Then.
Yeah. Because like,
Yeah, I
for
understand.
me, if you do like you do the problem, then you'd be like, is this right?
No,
No.
I understand. I mean, I would encourage you guys to do some collaborative studying to check solutions. I think that's a little bit more. It's a little bit more helpful for like drilling in the reasoning and problems.
If you could just put the answer to the final answer, you don't have to. Well, you
Yeah.
eventually show the word.
Yeah.
The other solutions, then you can at least see like how to do it.
That way, if I go through it and I get the right solution, then I'll do
Or you could just put the answer like
Yeah.
beforehand,
Yeah.
and then
Yeah.
like day before the exam, you put like the whole solution.
That could be it. All right, I'll try doing that. Yeah, that's fair. I guess the other question I have for you guys is for midterm 2, I am kind of juggling what format it's going to be. I had in class versus a take home. So I guess we'll do kind of an informal poll, like show of hands if you prefer an in class. Like you come in, it's done at the end of an hour and a half, you don't have to worry about it.
What would the advantages / disadvantages be of in class
Well,
versus take home? That's the main question.
I guess take home. I mean, I'm still gonna make it like a target of about an hour and a half in length.
Okay.
I'm not gonna be like, oh hey guys, here I threw all of chapter 6 at you. But I would say that it'll be a little bit less. Like a take home one is gonna be a little bit more in depth.
Sure.
Right.
Makes sense.
The idea that you it's like an hour and a half, but without the pressure of you know, if I don't finish this in an hour and a half, I'm usually screwed. Alright, so show of hands for take home format. Oh, well, that seems to be kind of a landslide.
Why not?
Peer pressure?
Try something different.
Alright, give that a shot. Fair enough. I think the day that I had picked out for that midterm is actually my PhD defense, so if I could give you all a little notes and not worry about proctoring an exam, that would actually be helpful. Okay, well then, I guess my last 5 minutes, let's do just a quick little, like, not an example problem, but like an application kind of like sketch out how we would look at a problem. Let's say, I mentioned before the control volume analysis is how we figure out, one of the ways we can figure out like how planes fly, right? Because planes are heavy, gravity does a lot of stuff, they try really hard to come falling out of the sky. And so the idea is, let's say we've got, a really, plane here with some weight, right? If we were looking at, what keeps this thing aloft, what sort of, angle of attack do the wings have to be at, or what speed might be a better one actually. Let's say, what keeps the plane aloft, right? What's ultimately the mechanism or the part of the plane that keeps it in the air? Right? The wings, right? They generate the lift. So what we're interested in figuring out is if it's staying aloft, sum of the forces in y, if it's in a stable state, we end up with lift minus weight is equal to 0. And all the lift is generated by the wings, like we said. So if we look at one of these wings, okay, and I think we do a little bit on foil theory in this class, and so we'll get into this a little more in depth. We draw a control volume around this wing. Let's assume that we've got uniform inflow into this control volume. Now note, the air isn't actually moving, but the plane is. So this ends up being a case of a moving control volume where we have a relative inflow velocity. So if V air is equal to 0, then W air here is equal to 0 minus V plane. Yeah? Since V plane is in the negative direction, since it being a positive number. And let's assume that the action of this wing is such, don't worry too much about what the wing actually looks like, that the flow coming out of the control volume is coming out at some angle theta, all right? And this is, so this is essentially the wing is redirecting some of the flow downward, okay? If we were looking at how to figure out what the, we've got, let's see, actions on the control volume, we've got the weight of the plane, right? So if we said sum of the forces in y equal to, if we're assuming steady state control surface, we would say rho v dot n dA, right? So what we would get is more or less the 0 at the inlet, right? There's no vertical velocity coming in, and leaving. What we would get is depending on, if we said like, all right, let's let the streamlines look something like this, right? What we would end up with is some area of the outlet here where the flow is exiting at an angle. So if we integrated over that area, we assumed that we have a constant V, which is equal to, in this case, negative V plane, that is the magnitude of the inflow, times sine theta, except now directed downward, so we end up with positive V plane, sine theta. Then integrate this over whatever part of the control surface has outflow at some angle. Then what we'll get is we'll say negative weight of the plane is equal to surface conservation of linear momentum. And so we say that it's conservation of linear momentum plus plane. Is this right? Yeah, I think the signs will fix themselves. Is equal to 0, and so we can say that the lift is going to be equal to, you know, blah 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 blah, the integral over the vertical component of the momentum, leaving the control volume only, right? So, for example, if we said here's how much the plane weighs, you know it's directed down out of the control volume at some angle theta, then what you could do is just simply solve for the V plane required to keep the thing aloft, yeah? So this is a really quick little outline of how you would use this to solve like a basic aerospace problem about making big hunks of metal fly. Alrighty, have a good fall study break, guys, and we'll see you on Wednesday, right?
So, did you find out today?
It's officially out of
Now I have more questions. In gravities, I won't do it for this team. The next two last.
Alright, cool.
It's nice and cold.
Yeah, I know, right?
Day that everyone wakes up. The day or something.
I'm both my mom.